Okay, in this video we're going to start Chapter 5. Chapter 3 was differentiation. Chapter 4 was applications of derivatives. And now we're going to start the other sort of half of the other side of the coin of calculus. And the first thing we're going to talk about is antiderivatives and indefinite integration. And the 4 bullet points, what you're going to get out of this section: you're going to be able to write a general solution to a differential equation, use indefinite integral notation for antiderivatives, use the basic integration rules to find these antiderivatives, and find a particular solution to a differential equation. Inverse operations. Most functions have an inverse. Like if I have x squared and I square root it. Squares and square roots are inverses. They will cancel and we're left with x. If I take some number x and first I multiply it by 3 and then I divide by the same 3, multiplication and division are inverse operations, as are differentiation and anti-differentiation. One of them undoes what the other does. So suppose you were asked to find a function, and now here it's capital F, whose derivative is f of x, and that's 3x squared. So what do we derive to get 3x squared? From your knowledge of derivatives, you'd probably say that, well, if we take x to the third and we derive it, d dx of x to the third is 3x squared. The function f, capital F, is an antiderivative of f. So our official definition here says a function f, capital F, is an antiderivative of function f on an interval I if f prime of x is equal to f of x for all x values in that interval. Note that this new function f, capital F, is an antiderivative rather than the antiderivative. To observe why, we have 3 functions here: f sub 1, f sub 2, f sub 3. If we derive f sub 1, we get 3x squared. If we derive f sub 2, we get 3x squared. The minus 5 derives away to nothing. The third one, the 3x squared, still derives to, or the x to the third derives to 3x squared, and the 97 derives off. So all 3 of these functions had the same derivative of 3x squared. In fact, for any constant c, if I take any function x to the third and add or subtract any constant, that's going to derive away, and we're going to be left with just 3x squared. So to account for this constant, the antiderivative is x to the third plus c, where c is just some arbitrary constant. Theorem 4.1 is just more about this new notation for this section. If capital F is an antiderivative of f on an interval I, then g is an antiderivative of f on the interval I if and only if g is in the form of g of x is equal to our antiderivative f of x plus our arbitrary constant for all x's in the interval, where c is just, again, some constant. Using Theorem 4.1, you can represent the entire family of antiderivatives of a function by adding a constant to a known antiderivative. For example, knowing that the derivative of x squared is 2x, you can represent the family of all antiderivatives of this function equal to 2 of x by this g of x. G of x is just x squared plus some arbitrary constant, where c is a constant. The constant c is called the constant of integration. Oop, I could have picked a better color. Constant of integration. The family of functions represented by g is the general antiderivative of f. And g of x equals x squared plus c is the general solution. Our general solution has that constant added to the end of our differential equation. A differential equation in x and y is an equation that involves x, y, and the derivatives of y. For instance, y prime equals 3x or y prime equals x squared plus 1 are examples of differential equations. So let's look here, and let me just back up real quick. When we derived, like x to the third, the steps to get our derivative is we brought our exponent down and multiplied 3x, and then we dropped our exponent by 1 power. So we multiplied by old exponent and dropped power by 1. To find the antiderivative, we sort of reverse these steps. To find the antiderivative, we want to raise the exponent by 1. Raise exponent by 1. Divide by new exponent. Divide by the new exponent. So there's our derivative and antiderivative general idea. So to solve this differential equation, find the general solution to the differential equation y prime equals 2. And you might think there's no x there with a variable or an exponent to raise up by 1. But with a 2, we could tack on an x to the 0, and it's not going to change anything. Because no matter what x is, anything to the 0 power is 1, 2 times 1 is 2. So there is now a variable we can feel comfortable with. Our rule says that we should raise that exponent by 1. It was 0 power, now it's x to the first. And we're going to divide by that new exponent 1. So our function y is going to equal 2x divided by 1 is 2x. And to make sure it's the general solution, we tack on our arbitrary constant. We add on c. And again, that constant c is just telling us there could be many different graphs that have this derivative. So all these lines here have a slope of 2, just like our equation. And remember, in y equals mx plus b form, the c, this constant, is just going to be our y-intercept. So right here, we have a constant of 0. This would be y equals 2x plus 0. If we have a y-intercept at -1, this would be 2x minus 1. This other equation, we cross the x-axis or the y-axis at 2. That would be 2x plus 2. So there's all the functions that are in that form. A little more on the notation for these antiderivatives. So when we're solving a differential equation in this form, dy dx of f of x, it's convenient to write it in the equivalent differential form, like we did in the previous section. What you're kind of doing, it's not exactly right, but it looks like we're multiplying both sides by dx. So we have dy equals our f of x times dx. The operation of finding all solutions of this equation is called antidifferentiation, or indefinite integration. And it's denoted by the integral sign that looks like an elongated s. The general solution is denoted by, here's y equals, what it comes after our integral sign is our integrand, the function we're working with. The variable of integration is given away by our differential. This is dx, so we're integrating with respect to x. After we perform the antiderivative operation, we have our antiderivative of the original f of x, and we add on our plus c, our constant of integration. The expression right here, when we read that in English, is the antiderivative of f with respect to x. So the differential dx serves as the identity x, or it serves to identify x as our variable of integration. The term indefinite integral is a synonym for antiderivative. Exact same thing. And at the start of this video, I did note that x squared and square root, squares and square roots are inverse operations. They undo each other. And that's what we see here in these blue boxes, our basic integration rules. If we take the antiderivative of some f prime of x with respect to x, we just wind up back at f of x, and we add on our constant c. And the flip side of that coin is if we take the derivative, d dx, derivative with respect to x, of the antiderivative of f of x, dx, we're left with just f of x. The derivative and the antiderivative symbols here sort of cross out, and we're just left with f of x. It says over here in the red, integration is the so-called inverse of differentiation, and differentiation is the inverse of integration. These two equations allow you to obtain integration formulas directly from the differentiation formulas that we already know so well. So we're just going to peek at a couple of them here. I like the trig function ones. The derivative of sine is cosine. So the antiderivative of cosine with respect to x is going to take us back to sine of x, and we add on our constant. Cosine of the derivative of cosine is negative sine. So the antiderivative of sine is going to be negative cos plus our constant of integration. Up above, if we derive any constant, we get 0. We derive constants out of existence, but if we integrate nothing, that's where our constant comes from. The constant multiple rule. When we derive, say, 3x, we drop off 3. When we antiderive some constant, we add an x to it, or whatever variable we are integrating with respect to, and don't forget your constant c. Here's the biggie, power rule. When we derive some x to the n power, we bring down the exponent, it becomes n times x to the new exponent of n minus 1, 1 less. And here's the antiderivative equivalent. The antiderivative of x to some power n, we raise the power by 1, x to the now n plus 1 power, we divide by the new exponent, n plus 1. And don't forget your constant of integration. And of course this isn't going to work when n is equal to negative 1, because if we raise the power by 1, we'd get to the 0 power, and we cannot divide by the new exponent of 0. So that's something we'll have to deal with later. Okay, example 2, we're just going to apply these basic integration rules. Describe the antiderivatives of 3x. So what is the antiderivative of 3x? You know, we have our constant multiple rule. We can pull that 3 out front. And we're going to have x, and I'll put to the first power. It's not going to hurt anything, dx. So when we find the antiderivative, we're going to have 3 times, raise the exponent by 1, x to the second power, and divide by the new exponent. Or you could write that as 1/2 x squared. And well, 3 times a half is 3/2 x squared. And we don't forget to add on our constant c at the end. Now, when we did some differentiation problems, we would start out with on our original equation. We might rewrite it to make it more conducive to differentiation. Then we did the differentiation and we simplified. And we have a similar process for integration. We're going to start out with an original integral. We might want to rewrite it to make it easier to perform this operation on. Then we will integrate and simplify what we have left. So here in the first one, we have the antiderivative of 1 over x to the third. Well, to rewrite that, let's give it a negative exponent. 1 over x to the third becomes x to the negative third dx. Now let's perform our integration. Raise the exponent by 1. We're going to have x to the negative 2. And we divide by the new exponent, negative 2. And we add our constant. And now let's get rid of that negative exponent. And there is a 1 in front of that x to the negative 2 power. The 1 is going to stay put. We still have our 2 in the denominator, and the negative sign we can just put out front. Now x to the negative 2 drops to the denominator and becomes an x squared. And we have our constant of integration at the end. In letter B, we have a radical. A lot of times when we were differentiating, we were writing our radicals in rational exponent form. So square root of x is x to the 1/2. When we integrate, raise the power by 1, x to the 3/2, and we're going to divide by the new exponent 3/2. And we add our constant. Remember, dividing by a fraction is like multiplying by the reciprocal. So the 3/2 comes up, becomes a 2/3 x to the 3/2 power plus our constant. Part C, trig function. Well, the rewrite, we can pull the 2 out front. 2 times the antiderivative of sine x dx. Okay, now we got to think, what do we derive to get positive sine x? Well, that's negative cos x. So we're going to have 2 times the negative cos of x plus c. And to simplify, we can multiply the 2 through. Negative 2 cos of x plus our constant of integration. Last one. Now here, if we rewrite this one, we will have the antiderivative. We can pull the 3 out front, and that will be 1 over x. we could have wrote it as x to the negative 1, but would raise the power by 1 to 0, and we can't divide by that new power 0. So we got to think back. What did we derive to get a derivative of 1 over x? Well, that was the natural log. So we're going to have 3 times. We derived the ln of x to get 1 over x. So when we antiderive 1 over x, we're going to get the ln of the absolute value of x plus c. And then we can just sort of distribute that through there, and we'll get our 3 ln of the absolute of x plus c. So the basic integration rules listed before allow you to integrate any polynomial. And the polynomial functions are pretty easy. Let's see here. You know, it looks like we don't have anything there at all. And, you know, if it helps you to remember, you know, there is a 1 there. 1 dx. And if we wanted to, we could have 1 x to the 0. X to the 0 is just 1. So when we take the antiderivative, we raise the exponent by 1 to the first power. X to the first divided by the new power is just going to be a lonely little x. But then he's got his constant of integration to keep him company. Here, you know, we have a quantity in the parentheses with the dx after. We could sort of, if you want to think about it this way, we could have the integral of the first term, dx, plus the integral of 2, the second term, dx. And while this is x to the first, when we take the antiderivative, we're going to get x to the second power divided by 2, or that's 1/2 x squared. Plus, this is 2, so to speak, x to the 0. We're going to just add a x to our 2, 2x. And then we have our plus c, of course. In this last one, you know, I won't, you know, give them each their own integral symbol and distribute the dx. Let's just do this term by term. First is 3x to the fourth. We're going to have 3x. It's now to the 5th power, and we divide by the new power, 5. 3/5 x to the 5th. Minus, we have 5x squared. 5x, we raise that to the 3rd power, and divide by 3. 5/3 x to the 3rd. Plus, this is x to the 1st power. That's going to become x squared, divided by 2, or 1/2. 1/2 x squared. And we add our constant of integration. Ooh, this one looks tricky. Rewriting before integrating. We saw problems pretty similar to this when we were differentiating. And the thing that sticks out to me on a problem like this is a single term denominator, just that square root of x. Let's break our numerator up into separate chunks. We have our first term as x, and we can put that over our denominator, the square root of x, or x to the 1/2. Plus, we have our second term 1 over the same denominator, x to the 1/2 dx. And this will simplify even a little more. We have like bases, x, with different exponents. So when we divide like bases, we subtract exponents. 1 minus 1/2 is 1/2, x to the 1/2. Plus, we can rewrite this with a negative exponent, x to the negative 1/2. And to stay consistent, that would be in parentheses dx. Well, now it's going to be a little easier to perform our antiderivative. This is going to be x raised to 1 power. X to the 1/2 plus 1 is 3/2. And we would divide by 3/2 or multiply by the reciprocal 2/3. Plus, our next term, x, we raise the exponent by 1 from negative 1/2 to positive 1/2. And we divide by the x, or divide by the new exponent 1/2, or, you know, multiply by the reciprocal 2. So let me move that over a bit, and we can just squeeze a 2 in there. And we don't want to forget our constant of integration at the end. Oh, and it's not a good day until we've done a trig function one also. Antiderivative, sine of x over cos of x squared. Remember our differentiation idea, or one of the tricks we used, was to sort of pull these apart and see what they look like as components. Denominator is cosine squared. Well, cosine squared is just cosine times cosine. And the numerator is just a sine x. So we can do 1 times sine x is sine x. Ah, now it's looking a little more familiar. So let's see, what's the reciprocal identity of cosine? Well, 1 over cosine is the same thing as secant. Sine over cosine is tangent. Secant times tangent. I remember deriving something that gave us the derivative of secant times tangent. And that something was secant. Secant of x, and don't forget to add the constant c. And that'll be a good place to stop this video. We can pick up the next video and finish off this section.